Yeah. Thank you very much for the kind words, Professor Santanu Rastogi and Professor Ravishankar Singh. Am I audible?
Yes, yes, sir.
Okay. So I am really thankful to you for the kind words. I don't know whether I deserve all these things or not. Let me come straight to the point. This week online workshop, it aims to discuss various aspects of research methodology for multidisciplinary perspective of physics. This topic is relevant in the modern era of research, and it is because of this topic I decided to talk today about the optical telescope, which are integral part of multi-messenger astrophysics. Because as most of you know that astrophysics is just one branch of physics, and multi-wavelength observation, observational facilities, how important they are, that will be the main emphasis of my today's presentation. This plan, which you are seeing on your screen, after introduction, I will basically try to tell you what are the multi-messenger observational facilities, particularly in India, where ISRO, Department of Atomic Energy, and Department of Science and Technology, they are mainly contributing to this. And then towards the end, before conclusion, I will definitely talk about what Professor Ravishankar Singh just mentioned, that this observatory where we are hosting India's largest 4-meter optical telescope, and in fact, some of your students of the department, they are already making use of this. So let me begin with what is basically astrophysics. Before I really start, let me mention one thing. This talk is basically intended to the students. So it's at a very elementary level. I'm not going in depth. It's basically to provide information to the students so that they know what are the opportunities which exist in our country. That is my main objective of this presentation. So with these, words, with this background, let me start. Astrophysics, as most of you know, that it's a physics of celestial bodies, and sometimes also people say that it's a combination of astronomy and physics. It's a physical and chemical processes and characteristics of galaxies, star, planetary system, interstellar matter, all these things. If we talk about, that's what we basically say, it's astrophysics. And why it is important, why it is very integral part of physics, because in physics we always talk about laboratory and then try to see what are the experiment we are conducting, but there are certain laboratory conditions which is present in the universe, but we have been not able to produce them on the earth. Just to illustrate that, that's why we call that astrophysics, it provides giant natural laboratory. For example, at the center of our sun, we know that we have very high temperature and density, and where thermonuclear reactions are taking place. And such high temperature and high pressure laboratory we have been not able to produce on Earth. That's why we say that it's a natural laboratory and provide unique opportunity to test our various physics laws. Also, if we talk about the stars, then we see, for example, neutron star. They are very, heavy. As you can see, as heavy as 10 to the power 12 gram per cc. That is the density of a neutron star. So we have that type of object, and also extreme. I'm not talking about the black hole, but extreme vacuum is also there, which we call interstellar matter, where density is of the order of 10 to the minus 24 gram per cc. And if we talk about stars and galaxies, then we are talking very large numbers here. As you can see, solar, generally if you want to go into CGS system, then one unit, what we call solar unit, it is 2 into 10 power 33 grams. So in case of stars, the mass range is 0.1 to few hundred solar mass. But if we talk about the galaxy mass, then it's 10 to the power 12 to 10 to the power 13 solar mass. So you can see how giant these laboratories are, and that's why we say that such laboratory do not exist on Earth, and that's why it's very important to study these celestial objects using our known physics laws. Few examples which are well known, I will just try to repeat, that what are the main, in a sense, advantage, many advantages astrophysics has given to the society. One of them I am highlighting, as most of you know, that the Kepler law, planetary orbits, how it functions, physics law, it was established as early as 1605 to 1609. But this law, what we say pure scientific laws, it took almost, as you can see, more than 300 years to convert these things, to use these laws so that you can launch the satellites, this thing, which was done first by USSR in 1957. And its advantage and benefit and growth of the knowledge is well known. So this is, in a sense, contribution of astrophysics to the society. Also, this slide I'm trying to just tell you how briefly what we have learned during last 300 years with the telescope. In the beginning, we thought solar system is the center of our, universe. But as soon as Galileo used in 1609 telescope, and then he saw that there are bodies which are revolving around planets, then immediately question became that that sun cannot, Earth cannot be at the center of the universe. Then people thought, okay, if it is not sun and Earth, it will be our solar system. That is, sun is at the center. But today, with all various knowledge, we know that sun is off-centered. This is the core center of our Milky Way galaxy. Sun is located about 28,000 light years away from the center. So like this, there are many things which we learn, and this you can say the dimension of our galaxy, which is about 1 lakh light years. So if light travels from one end to other end, takes roughly about 1 lakh light years to cross from one side to other side. And this knowledge we just learned recently, with our observation things. Other things which we really, in fact, astrophysics, that's what we say that if you want to really discover many new things, this is such a laboratory where you have enormous potential. This is one example, as you can see. It's a very small, tiny field, as you know, out of 360-degree sky. It's a 2 arc-minute by 3 arc-minute sky, and it's a very deep field taken with Hubble Space Telescope, which very clearly demonstrate that there is a full of galaxies. These are not painting or somebody has made some sort of design. These are natural things, and we have only one stellar object which you see as a cross here. That's the only stellar object. All other things which you see, they are real celestial objects, and they are full of galaxies. And in fact, today we know that 95% of the matter is unknown to us. What is the nature, it's dark matter, or what type of matter it is. So it means a lot of potential is there for the discovery if we try to study astrophysics. Now, let me just introduce few, what I can say, scales which are used. One is just I mentioned light year, but most astronomers say astronomical unit, which is the average distance between sun and earth, and that number is given here. It is one astronomical unit is 1.5 into 10 power 11 meter, and you can convert light year and parsec, all those things. That's how the distances are measured in the universe. Also, this slide will just tell you that in our solar system, if we compare, then there are this column, as you can see, the object name, and this column tells us what is the intrinsic brightness of the celestial object, and this tells what is the fraction of the photon which is reaching on Earth. And it is simply because of the fact that they are located at large distances, and most of us, we know that it's 1 over r square law, which follows, And if we see, for example, there are bright Cepheids which are, 20,000 times more intrinsic energy they have than the sun. But when it reaches to the earth, compared to sun, what we say, so we receive 10 to the power minus 16 time of that, flux. It is mainly because it's located at typically about 200 kilo light year away. So because of these distant objects, we are not able to receive large light, and that's the one of the obstacle while we are trying to observe these celestial bodies. This another example which just says that because of the large distance, as we know that angle is nothing but linear size divided by the distance. So if you divide the linear size of any object with the distance, since distances are very large, the angular size of most of the celestial bodies are very small. In fact, they are in milliarc second, micro arc seconds. But in our solar system, they are arc seconds, which I have just given in this table. Our angular diameter of the sun is about 32 arc minute. But compared to that, if we see, we have very small angular size, and it's again because of this distance. In fact, our nearest star, which is Alpha Centauri, it has a angular size of only 0.0071 arc second. It means 71 milliarc second. So they are very, angular size is very small. It's basically because of enormous distances. Now, if we compare our laboratory physics and this, then we are having disadvantages mainly because of the fact that they are located at a large distance. And only our laboratories comparison, you can see, like we have meteorite sample, lunar material, space mission of various space agency. But all these things are limited just only to the solar system. We have learned a lot about our planetary system, but limitations are posed due to enormous distances of celestial bodies. And physical condition of these celestial bodies cannot be tempered because they are naturally occurring something. So how to, that's a challenge in astrophysics, and that's where how telescope and detectors and multidisciplinary physics comes into picture. I will try to highlight them at appropriate points. So this slide actually, astrophysics, that's why we also call it is an observational science. So if you see a celestial object, which could be like planet, any galaxy, or any star, and what are the messenger, which I gave you multi-messenger. Till a few years ago, we were just talking about mostly electromagnetic radiations and neutrinos. But now it is well established that gravitational waves are also there. So while we say messengers, then it means the wave which is carrying information from these celestial bodies to us, that is on the ground. And a detailed description of this is given in a journal editorial in 2018, that what are their importance and why they need to be studied at various wavelengths. So this just cartoon, it shows that after traveling distances, it enters into Earth atmosphere and it's a wave. And as most of us, we know that wave is characterized mainly by amplitude and phase. So when it enters into the Earth atmosphere, amplitude will be affected, which causes attenuation, and phase, when it is affected, it causes blurring in the images, what we call degradation of sources of images. And these are the things which are becoming part of technology today, how to improve them. And that's what partly I will touch upon in my next slides. And as you can see, Earth atmosphere is very, very valuable for us. That's why we are here. Although in Corona period we are not see each other physically, but virtually we are able to meet. But if you see the total electromagnetic spectrum of our, it shows. So it's a very tiny portion of the electromagnetic spectrum. One is located in the visible, other one is in radio, and some part of the near IR, which we can observe from ground. All other radiations, they are blocked by our atmosphere, and that's why till 40-50 years ago, only we had information based on optical telescopes, that is optical and near IR, as well as the radio, because those were the facilities which were observed from the ground. Rest we were not able to observe. And rest after launch of satellite, now we have gamma rays, X-ray, and UV payload, which are providing valuable information about these celestial objects. And when they are combined, these what we call multi-wavelength observations, when they are put together, then they tell us what type of these celestial objects and what are the physics, taking physical laws which are governing the processes in these celestial objects. And that's why we have space astronomy and ground-based astronomy. And this slides basically explain why we need, because these objects, only thing which, as an observer, which is in our hand, these photons which we are able to receive either from space or Earth. But if we have, let us say, black body, thermal radiation, then we know that its spectrum will be like, black body, and it will be characterized by these curve, like 10,000, then it will be something like this and this. But if we have synchrotron radiation, then the energy distribution is quite different. So it means unless we have multi-wavelength observations, we will be not able to find out what is the source of energy in these celestial objects. Like most of the galaxy people nowadays say that center has black hole, accretion disk, then X-ray is originating, and many processes are taking place. So to decipher these things, we have to have multi-wavelength observations. Now I will try to briefly mention you some of the mega projects which Indian, Space Department of Space, ISRO, Department of Atomic Energy, and Department of Science and Technology, they have taken, and which are, I will say, it's a potential and opportunity for the students to know about it, and also there will be opportunity to make use of them, either by observing them or becoming integral part of them. So AstroSat, as you know, it was launched on September 28, 2015. It has already completed 5 years, and it was operating in visible, ultraviolet, and X-ray region, and it was the first Indian multi-wavelength astronomy satellite. It has 5 instruments, and details and all those things I'm not going to describe here. They are well documented in two special issue of Journal of Astronomy Astrophysics, one published in 2007, and other recently, just few months ago, it is published, 5 years in orbit, science result, volume 42, 2021. Similarly, we have space-based astronomy projects, Aditya, Chandrayaan 2, which are progressing well in the laboratory. And in fact, their information is also given in current science published in this article. This is one of the, INSIST. It is, in a sense, next generation of UV telescope, which is under planning. In fact, IIA is leading it. And this project, seed money has been given by ISRO, and it's at the developmental activities. And once it becomes, India will have a unique place in the global astronomical community in UV astronomy. This part definitely I will talk about India's largest site telescope at Devastam. So I'm skipping here. I will just say that one new facility which is coming us by PRL. They are installing 2.5 meter telescope at Mount Bravo, and it will start functioning very soon. Then you must have heard TMT, which is 30 meter projects, and it is also 10% participation from India. In India-based neutrino observatory, these details are given where CS means current science, and year and volume number and page number, they are given here. About LIGO also, a lot of progress is taking place. At radio wavelengths, well known, we have NCRA GMRT and OT radio telescope, square kilometer array. And at other wavelengths also, India is taking, I will say, they are involved in establishing mega facilities either on their own or in collaboration with the other country. So these details are given. I would like to just conclude with this, that as you can see, the upcoming facilities, they range from solar system to various wavelength. So all these initiatives take long period, in fact, few decades, and need dedicated teamwork, but provide golden opportunity for the growth of modern observational astrophysics. So this is just like I can say that summary of what the mega facilities, which is where India is involved. Now I will come to the main topic, which is why was the field of working, that is optical telescope. So before I go to describe telescope, let me tell you why optical astronomy is very important. I mean, there are many ways of narrating it. I will just try to cover in brief. As you know, physical processes, we have spectral lines, and that's why spectroscopy is very important too, because we get the energy distribution, and that tells us what are the lines and what continuum, and if lines are originating, what are the physical conditions. And most of these, what we say diagnostic lines, they lie in optical and IR region of the electromagnetic radiation. That's why in the era of multi-wavelength astronomy, optical and near IR astronomy is very important. And a few examples like X-ray sources.
These are the things. It was,
yeah.
Yes, please go ahead. Please
Yes.
go ahead.
I'm unable to operate my yeah. So now I will talk about the optical telescope. They are, as I told you, that optical window is very important, and for this we need telescope. And just to introduce, I mean, you know, telescopes are as old as human civilization because we all contain two eyes and they act as a telescope because its optics and detector and analyzer, everything is there. But you know, a giant, I will say, improvement took place in 1609 when Galileo, about more than 400 years, in fact, made celebrated International Year of Astronomy in 2009, which first time saw the planets and, in fact, really shows the importance of instrument, precise measurements, and those things. And with recent developments in computer, electronics, and other areas, they have contributed significantly to the growth of optical telescope detector and image analysis. And that's what I mean. It's a multidisciplinary and wavelength things. I will just try to say how we are, as in the introduction, I told you that most of the celestial objects are located at a far distance. So we have very angular size of those objects are always very small. The question is how to resolve them. Definitely, telescope have two functions. One, they improve resolving power. Other, they improve light getting power. In case of resolving power, as you can see, before till 1609, human eye was there. So we had resolving power of something like close to 70, 80 arc second. But as soon as the Galileo used the telescope, as you can see, 1.22 lambda by d, which is well-known formula in the optics, that tells us that, its resolving power improved drastically, and it was a quantum jump. But as you can see, of course, the size increased, but resolving power of the objects could not increase because Earth atmosphere is not stable and it degrades the imaging system. But as soon as HST was launched, again there is a quantum jump in this. So in fact, Earth atmosphere, what we call blurring, it produces 1 to 2 arc second. Sometimes we find very good values, which are of the order of 0.3 to 0.5 arc second. And at such location, that's where you would like to put your telescope, which is very expensive, but at the same time, they will provide you very good quality observation. Nowadays, multidisciplinary things which are coming like adaptive optics, interferometry, they are providing better resolving power, but they are the future. Other things which I would like to briefly tell why always what we say site characterized before launching the telescope, or you might be knowing that most of the telescopes, they are anything larger than 1 meter. Generally, they try to put at a high location on the hilly region. And the main reason for this, I will try to highlight through this slide. What is the purpose of telescope? Is the light gathering power if we define by A. Then it's given by simple formula where T is the loss due to optics and detector, because any optics or any detector, they will have some light loss. D is the size of the, let us say, telescope. And if we compare with our pupil size, then we can see that for a 4-meter size telescope, light gathering power, increases by 25 to 150,000 multiplied by the transmission loss. Other thing which is very important, if you see, because most of you know that error analysis is very important while we talk about in our data image processing and things like that. And there it comes signal to noise ratio, where it shows very clearly that improves with the integration time. But at the same time, it also depends what is the sky brightness. For example, during daytime, we are not able to see the stars. It doesn't mean that they are not there. They are there, but due to sky brightness, we are not able to see. And also the angular size, which is formed by the image. If it is a point-like source, it means we have more energy concentrated in a small area, then we are able to see better things and fainter things. So that's why characterization becomes essential. And it becomes also essential for the technical specification of the telescope, that what quality of the optics you need. So in fact, now I will try to briefly tell you that how, from I to today's era, detector, because any image we take, today if we are talking about all of us in our mobile, we have, a built-in camera, which is CCD camera. But if you talk about, 19th century, then I was there, and then we came to the era of photographic film. It had its limitation, and then we came to photomultiplied tube. One term which I would like to just mention, what we say quantum efficiency, that if 100 photons are falling, how many of them detector is able to detect? And that is a very important parameter. And in case of eye, our retina has just less than 10% detecting power, but in a very narrow wavelength range. But during use of photographic films, these things improve, but not significantly. Photomultiplier tube, it drastically improved. In fact, this increased our quantum efficiency from few to 35, 36%. But I will say a major improvement come due to the solid state device. It's a charge coupled devices, and it has a lot of positive things. Only thing which I would like to conclude saying that you can see that the detector, if we have 1 meter mounted on 1 meter telescope, it performs as good as a 4-meter telescope with a poor detector. It means photographic film. So this you can see that how important detectors are. But now CCDs, they have reached to a almost saturation, above 96, 97%. So we don't have much hope that from detector point of view, we are going to gain quantum efficiency. But T, as you see, light glasses, we have very good quality of glass, mirrors and other things, where again, we have reached to a limit. So how to increase if we have to do, that's where technology is coming to picture. We have to use today's technology to increase the size of the telescope, like what some of you might be knowing that 30 meter, 20 meter, these type of telescopes which are under built, they are not single piece, and that's where technology is playing a major role. I will say how, image processing has improved. This, as you can see, as most of us, we know that short camera, fast camera, we say not fast camera, slow camera, all these things, terminology are used also in telescope while we are designing. And this tells basically this is a low resolution image. This is a better resolution image. Then again, as you can see here, the one resolution you can infer from there. that the plate scale is 67.5 arc second per millimeter. Here 7.2 arc second per millimeter. In this case, as you can see, it has much better plate scale, and this is the power of image processing. So this clearly shows, in fact, in 1970s, this picture displayed as a revolution in the ground-based imaging, that how these technologies, they are telling us more about us. And you can say here what you see like a blob. Here we see that some diffuse objects, but they are clearly resolved in the charge coupled devices images because of better resolution and image processing techniques, which is in a sense, I will say, contribution of the today's computer era. This is another thing. This ground-based facilities, they were never able to resolve center of an object like globular cluster, but HST first time it resolved and tell us what are the type of stellar objects which are populated in the center. So these resolutions are very important in astronomy, and this just shows. Now I will briefly spend few minutes on Devasthal. So before installing, this is tell us where it is geographically located. As most of you know, it is in Nainital district, and its aerial distance is about 22 kilometer from Manora Peak, and by road it's about 57 kilometer. So in fact, about more than decade-long survey, it established that what are its characteristics. And important thing, if you see, its topography is such that it's a very conducive for the laminar airflow. And this is very important point. I mean, if we have laminar flow, it means the turbulence, phase of the wave, electromagnetic wave or whatever wave is coming, it will be not affected drastically. But if we have chaotic motion, then phase will be affected. So that's why Devasthal is very, because of topography, it's provide very good observing condition, which I will highlight in the coming slides. And finally, these are the 3 telescope, 3.6 meter, which has been established. This is 4 meter ILMT, and this is 130 centimeter fast telescope. In fact, a full article, it has just appeared in Resonance, and its details are given here. It's published by Sagar Academy. It's a Resonance journal for science education. And only thing which I would like to mention here that in 3.6 meter, Belgians have contributed 2 million euro cash, which is equivalent to about roughly 10% of the project cost. So this is one project where foreigners are putting money in India. In ILMT, in fact, contribution of ARIES has been infrastructure only. All the instrument and detector and technology, they came from all those things were, from Europe plus Canada. These two countries, region, they have contributed, and this is the telescope which is there. I would like to just mention a few things about 3.6 meter. As you know, the telescope, basically whether it is fast camera or slow camera, it is decided by science requirements. So based on the community demands, it was designed as a f9, means its focal length is 9 times 3.6. So as you can see, roughly 32 meter focal length, but it's a very compact. As you can see, it's a combination of 2 mirror, M1 and M2. And as you know, with simple optics, if you put them in a proper separation, then we are able to achieve. For example, M1 is only f2. It has 7.2 meter focal length, and M2 is designed such a way that if we put M1 and M2 together, we get a telescope of f9 focal length as long as about 32 meter. And all other things are like it has at the, because telescope will collect only photons to analyze, we need back-end instruments, and this has 3 focal plane instrument, 2 at the side port and 1 as the main port. and these details are already published. And if someone is interested, I mean, some of the people who are already visiting, they may see it closely. These details are in fact published by Brijesh Kumar, uh, by Amitesh Somar in these years after installation. This telescope was uh, technically activated on 30th March 2016 from Brussels by premiers of both the country, Belgium and India. And in fact, there are some publications which even Gorakhpur University department, after using, they have published last year. And these are some, science results which are published. Few things I will just mention. This is really, it's a quite unique type of facility. It's capable of providing 0.4 arc second resolution. And good thing is that because of the location and topography, for a good fraction of time, sub-arc second images one is able to get with this telescope, and it's performing very well after the inauguration. There are technical hitch and other those things are very common in such a complex instrument, but they are attended timely and it is performing very well. So this is one picture which shows about the telescope. Now I would like to summarize and conclude what I just said, that modern ground-based technology and Hubble Space Telescope has provided us with unprecedented angular resolution and brought universe 10 times closer to us. Because we know that HST provides 0.1 arc second type of resolution. From ground-based, we get about 1 arc second. So it means 10 times more, better resolution means universe has been brought 10 times closer to us. With innovative technology like thin segmented mirror techniques, advancement in computer and electronics, the telescopes have become cheaper than they were 30-40 years earlier. CCD has virtually become an optical detector because of very large quantum efficiency, which is close to above always 94-95% in a good wavelength range. As a result, ground-based optical telescope as big as 40 meter are being designed. 100 meter people are already planning. Hence, it's always required cutting edge of the technology, and that's what I meant, disciplinary interaction. And Devasthal, I have already mentioned about its telescope. It's located, it's located in the northern hemisphere. So its uniqueness is it has a longitudinal advantage. It means between Spain and Australia, if you see, Australia is in east and Spain is in west. It's located almost in the middle. So it's provide, in fact, very useful observation for time domain astronomy like supernovae, transient astronomy, what we call. And that's why it's very important, there was the location, because modern, capable of providing very good, quality observation. And this just tells briefly about its parameter, that it's a really thin mirror technology. First time, it has been, such facilities are installed in the country. It's based on active optics technology, and sub-arc second, it's able to analyze. And this I have just mentioned. Some of you are also using it. Care taken, this is very important, because generally while you build your building or house, if you don't take proper care, it degrades the thermal environment of the surroundings. That has been taken care. As a result, it's able to provide very good 0.4 arc second images it has been able to provide. And seeing has not degraded, atmospheric conditions were not degraded at the site in the process. And these are some capabilities, and we are quite confident that it will contribute significant to the growth of not only our country, but to the global astronomy. And this is 3.6 meter, a closer view. Thanks. And some of you, if you visit, this may be attraction. You can see 120 degree of Himalaya from the place. Thank you.